So, just have a look on this that flux linkages for phase A, phase B, phase C, lambda A, lambda B is equal to 0.4605 into this whole matrix, right, into IA, IB, IC. This is equation 63. Therefore, symmetrical inductance matrix L is given by, right. So, just hold on, by this expression L is equal to 0.4605, then put them in the matrix form in millihenry per kilometer, right. Now, for balanced 3 phase currents with IA as a reference, this IA as a reference, IA, IB, IC, they are 120 degree phase shift difference. So, alpha is 1 angle 120 degree, hence alpha square will be 1 angle 240 and alpha cube is equal to 1, right, you know this. Therefore, you can write that IC is equal to, right, actually it is leading IA by 120 degree. So, IC is equal to alpha IA, that this one, right, and IB actually leading IA by 240 degree, that is your alpha square. Therefore, IB is equal to alpha square into IA. This is equation 65, right. So, this expression for IB, IC, right, if you substitute here, if you substitute in this equation, just hold on, if you substitute here IB expression for IB, IC here in equation 63, right, then what you will get, that is why writing using equation 63 and 65. So, what you will get? You will get LA is equal to lambda A upon IA 0.4605 log 1 upon r dash plus alpha square log 1 upon DAB plus alpha log 1 upon DCA. This is equation 66. Similarly, lambda B is equal LB rather, LB is equal to lambda B upon IB is equal to 0.4605 then into alpha log 1 upon DAB plus log 1 upon r dash plus alpha square log 1 upon DBC. This is equation 67. Then LC is equal to lambda C upon IC is equal to 0.4605 into alpha square log 1 upon DCA plus alpha log 1 upon DBC plus log 1 upon r dash. This is equation 68. So, equation 66, 67, 68 it shows, they show that this inductance LA, AB, LC are not real quantity, right, that are not equal. They are, first thing, they are not equal due to mutual inductances they contain, because they contain imaginary parts. So, these are not real quantities, right. So, that means all LA, LB, LC they will be different. So, to make the inductance of phase A, phase B, phase C more or less same, right, we go for a methodology for transmission line, that is called transpose transmission line, right. So, in that case, suppose you have a conductor, suppose this way triangular configuration is taken, say this is A, this is B and this is C phase, current in conductor phase A that is IA, phase B it is IB and phase C the current is IC. Distance between phase A and B as usual it is DAB, between phase B and C it is DBC and between A and C we are writing DCA, right. Now, for this is the transposition cycle of 3 phase line, this is section 1, this is section 2 and this is section 3. Now, what will happen, that you take, for example, you take first, this is conductor A, this is conductor B, conductor C. So, consider the section 1 first. So, this is conductor A, conductor B and conductor C as usual, current through conductor A IA, through conductor B IB and through conductor C IC. Now, what will happen, this is the first section 1 say. Now, in the next section, what we are making it section 2, that it will be in cyclic order, right. That means, conductor A was supposed to be here, but instead of that it is occupying the position of conductor B, right. So, it is coming here conductor A, right, and and similarly, if we do not take transposition, conductor A should have been here also in section 3, but ultimately it is taking the position of conductor C. So, conductor A, that means in 3 different sections, that means one cycle, that because 3 phases. So, therefore, it is changing it, that position of the conductor is being changed, right. So, it is A, B, C. Now, if you take like this, that your suppose it is A, it is B, and it is your C. So, this is your this is A, B, C, this is A, this is B, this is C, right. Now, in the next section, the conductor position actually is changed. That means what? That it will be, again I am drawing it for you. So, say this is here now you rotate it in clockwise. So, this is C, that initially it was C is occupying position of A. So, it is coming here C, A is occupying position B. So, it is going to here, and B is occupying its position, your what you call C's position. So, here it is B. So, that means here you take in clockwise direction, right, clockwise direction. Therefore, next section it is coming CAB, right. Similarly, for the last one, again you rotate it, this is your conductor like this, 3 conductors. So, B will occupy the position of here, it is coming to B will be here, C was here, now C will be here, now A was here, now A will take the position of B in the next. That means, it will be again in clockwise, A, B, your what you call B, C, A, right. Here it was C, A, B, it is starting from here, it is B, C, A, look at that, it is B, C, A, right. So, the from A, B, C, this is you start from here A, B, C, next just B, C is occupying position of A is occupying its position at B, B is occupying its position at your what you call that C's position, B is coming here, starting from here only CAB. Similarly, third one also it is BCA, right. So, this is actually is called what you call the transposition of that your what you call conductor, and that is, and if you say that it is at regular interval, in reality if it is a regular interval, then average inductance will be more or less same. Now, what is happening, that asymmetrical spacing give complex values of phase inductances, which we have seen just now, right, which makes the study of power system difficult. However, one way to regain symmetry in good measure and obtain a per phase model by exchanging the position of the conductors at the regular intervals along the line, such that each conductor occupies the your original position of every other conductor, right. So, this way we will go for transposition. That means one cycle, that means 3 sections, this one and this one, right. So, in that case what will happen, that such exchange of the conductor position is called the transposition, right. So, transposition is usually carried out at switching station, when that means its substation, right. So, a complete cycle is shown in figure 9. Figure 9 means this one, this is your, this is figure 9, just now I explained, this is figure 9, right. So, this arrangement causes each conductor to have the same average inductance over the transposition cycle, because we have conductors every in three sections or conductors their position is getting changed. So, expected that average inductance will remain same for all the 3 phases, right. Therefore, to get the average inductance, we will make L is equal to 1/3, then LA plus LB plus LC, right. This is equation 69, right. So, or L is equal to 0.460 log dm upon ds millihenry per kilometer. This is equation 70, where all these things we have defined before, where dm is equal to dab into dbc into dca to the power 1/3, and ds here is equal to just r dash, that fictitious radius, right. So, this will be more or less your what you call all the phases inductance will remain as L. So, that is the advantage of transposition, right. So, next one is Next one is inductance of 3-phase double circuit line, right. So, in this case again it is section 1, section 2 and section 3, right. So, here it is A, B, C, I mean it is actually double circuit line, that means in each phase there are 2 conductors, right. So, A, B, C, here also other conductor in phase A is A dash, then B dash, then C dash, right. So, and distance this A C dash is D1, that means B B dash is also D1, C C dash is also C to A dash is also D1, right. Similarly, your A to B dash is equal to D2, that means B to A dash is also D2 because from symmetry, right, and A to A dash is D3, that means C dash to C is also D3, right, and between A and B, distance between phase A and this conductor A and conductor B, it is D. Similarly, conductor C dash B dash, right, and B to C it is D, and A to C it will be D plus D. So, 2D, right. Now, same as before, if we change this what you call, this is that section 1, this is section 1, right. Now, in the section 2 it is CAB. So, here also it is changed, that CAB. So, C to C dash, A to A dash and B to B dash, right. So, this is CAB, here also CAB, but 2 conductors are there in each phase, that is why C to C dash, A to A dash and your B to B dash, right. Similarly, in the section 3 it is BCA, right, just now we explained this, right. Therefore, here also BCA, so B to B dash, then A to A dash and C to C dash. That means, if it is a double circuit line also, then section 1, section 2 and section 3, this will be the configuration, right. So, this is actually figure 10, the arrangement of conductors in a double circuit 3-phase line. Now, a 3-phase double circuit line consists of 2 parallel conductors for each phase. I told you that A and A dash, there are 2 conductors, they are in parallel. Similarly, for B B dash, similarly for C and C dash, right. So, generally it is a common practice, right, to build double circuit 3-phase lines of greater reliability and higher transmission capacity, because in each phase if you have 2 conductors in parallel, right, first thing is, so their resistance will be half in each phase, that is the thing. Second thing is that inductance means the reactance. So, 2 parallel conductors in each phase means the reactance inductance will be half, hence the reactance also will be the half, right. Therefore, that means if it is so, that it actually increase the maximum transmission capability, right. So, to enhance the maximum transmission capability, it is desirable to have a configuration which results in minimum inductance per phase. We want inductance should be minimum, because for transmission system resistance is quite low, I mean very low compared to your reactance. Therefore, we want that inductance should be less, hence the reactance also will be less, right. So, this is possible if mutual GMD is low and self GMD is high. We have seen, no, just I am taking only that term, that whenever that expression is coming, that log of function of log of dm by ds, right. If you can reduce dm, right, and if you can increase ds, so it is dm is low and it is denominator is ds is high, means it is a 1 upon, it is your what you call. So, overall ds is high, dm is low, ds is high, then overall this dm by ds ratio will be much low, hence this quantity will be lower, right. So, if you make so inductance will be less. That is why if mutual GMD is low and self GMD is high, then only it is possible, right. Therefore, so that figure 10 I showed you the 3 sections of the transmission cycle of a double circuit 3-phase line, right. Now, to calculate the inductance, it is necessary to determine DEQ or geometric mean distance. GMD first you have to find out, right, and then self GMD, both the things you have to find it out, right. First GMD and then self GMD. Now, to do this, I have to go to this figure again, right. Now, you know, earlier also we have seen that dEq will be dAb into dBc into dCa to the power 1/3, that is say equation 71, right. So, dAb, that means that mutual GMD between phase A and B of section 1 of the transposition cycle, right. So, if you see that dAb, that is your A to B, right. So, it will be your what you call that first you taking in between AB and AB dash, right. Basically it will be in between phase your dAb means phase A and phase B. So, only you have to consider your AB and A dash B dash, right. So, dAb is D, right, and then your what you call dAb dash, actually it will be something like this. If I explain, it will be clear, just hold on, right. Just hold on. Suppose your D, just one I am showing you. Suppose you have that you want to find out dAb, right. dAb is equal to, right. So, is equal to your, I am making in my way, dAb is equal to, first you take A to B, say I am giving it, this is your small d suffix AB, right, then into d A to B dash. So, d A to B dash into, right, again this one is coming d A dash B, because it will be in phase A and B only, phase A 2 conductors, phase B 2 conductors, right. So, it will be d A dash B and into it will be d A dash B dash, right. Now, this dAb, your dAb is equal to d, this distance is d, therefore, it will be capital D, rather capital D, right, and your dAb dash is equal to small d2. So, it is d2, right, then dA dash B. So, dA dash B, again it is d, dA dash B. So, again it is d and dA dash B dash, and here it will be power should be 1/4, because 1 2 3 4. So, it will be your 1/4, right, and dA dash B dash, dA dash your dA dash B, where it has gone, dA dash B is equal to d2, sorry, dA dash B, dA dash B, this one, this is AB dash and A dash B, they are same symmetrical, right, they are same A dash B. So, this should be is equal to your d2, right, and d A dash B dash, that means this is equal to d to the power 1/4, right. That means it is coming, that is your d into d square and d2 square to the power 1/4 is equal to d dt half, right. That means your if you have, you should not have any confusion, things are simple, that is your dAb, actually dAb is equal to capital D, then your dAb dash is equal to, it is d2, then your dA dash B, A dash B, that is equal to your A dash B, that is your is equal to your d2, right, and dA dash B dash, right, A dash B dash, that is also is equal to capital D, right. So, see how many mutual possibilities are there, 1 2 3 4. So, it will be 1/4. So, ultimately it is coming d d2 A to the power half, right. That means, that is why I have written here that your d dt2 into 1/4 is equal to d d2 to the power half. So, dAb and dBc, they will remain as same thing, because A and B happening here, B and C, A and B happening in this region only, in this region. Similarly, your B and C, it is happening in this region. So, same symmetrical, therefore, dBc dAb is equal to dBc dd2, these two are same, Now, when you think about dCa, that means here it is A dCa, right, AC dash A dash C, dCa, in that case it will be something like this. Now, you take your dCa, right. So, in that case what will happen, that your dCa, capital dCa is equal to look at this one, right. So, it is first I have to take your DAC, right, then your your what you call AC dash, DAC dash, then your D, your where it has gone, ACCA, then DCA dash, right, and next one is your A2 DAC, then DAC dash, then DCA, same thing, right, and your DCA dash, right. So, in that case your same thing it will be DAC is equal to your 2D, DAC will be 2D, this total distance, DAC dash will be D1, D your C, here it is DCAC and DAC dash A dash, right. Then DCA CA dash, D where it is gone, C A dash, it is also D1 and it is also 2D, right, to the power 1 by 4, to the power 1 by 4. So, ultimately it will be 2D into D1, right, to the power half. So, here also it is coming 2D D1 to the power half, right. So, that means this way I mean when you will compute all these things, right, that DAB, DBC, DCA, there should not be any confusion, right. Just to consider all the possibilities between conductors in two phases, right. So, ultimately DCA will be 2D D1 to the power half, right. Therefore, this DAB, DBC and DCA, all these expressions you put in equation 71, right. So, in this case if you put, it will be DEQ is equal to DD2 to the power half into DD2 to the power half into 2D capital D D1 to the power half or whole to the power 1 upon 3, right. So, after simplification DEQ will 2 to the power 1 by 6, then D to the power half, then D2 to the power 1/3 and D1 to the power 1/6. This is equation 72, right. So, all the cycles only, and in all the cycles that conductor actually changing their position. So, DEQ will remain same for other two sections also. I mean these two sections also, that DEQ will remain same. So, even after transposition DEQ will not change, it will remain same as section 1, right. So, section 2 DEQ and section 3 DEQ, they will remain same, right. Now, after this one has to find out the equivalent self GMD DS, right. So, it can be given as DS is equal to DSA self GMD for phase A, DSB means self GMD for phase B and DSC means self GMD for phase C to the power 1/3. This is equation 73. So, I have written here for phase A DSA is equal to self GMD in section 1 of phase A, that is that conductors A and A dash only, right. So, in that case DSA, if you look into this, right, if you look into this one, right, for it is your only for phase A. So, in that case one will come, no, I mean if we write like this DSA, if we write like this, so one will, I am putting it this way, say DAA, then DAA dash, right, into your DAA dash into your DAA into DA dash, then D A dash A, put this way, D A dash A into D your A dash D A dash, right, to the power 1 by 4. Now, assuming these conductors, all these phases, they have the same radius, they have the same radius. That means the DAA will be your R dash, right, then DA dash, DA to A dash, it will be your D3, then DA A dash A, d A dash A, again it will be d3 and again d A dash, that means again r dash to the power 1 by 4. That means this one will be r dash means r dash square and d3 square, that means this one actually will become r dash d3, right, to the power half, right. So, this way you will find out your self GMD of phase A, right. Similarly, for phase B also same thing will come, r dash d1 to the power half, and similarly when you will find DSC in the similar way, right, it will become your r dash d3, all the time 4 possibilities will come, but it will become r dash square d3 square. So, ultimately r dash d3 to the power half. So, DSA, DSB and DSC, all these 3 self GMD you have got, right, and then you substitute that expression ds is equal to your in this expression, that you substitute here in this expression equation 73, you substitute DSA, DSB and DSC to the power 1/3, here you substitute. If you substitute, then you will get this expression ds is equal to, write everything whole thing to the power 1/3 and then simplify. So, ds is equal to r dash to the power half, then d1 to the power 1/6 and d3 to the power 1/3. This is equation 74, right. ds also remains same in each transposition cycle, because the position change, but there will be no change of ds also, right. dm and ds there will be no change in other cycle, right. So, over the transposition cycle, so they will remain same. So, you need not calculate your dm and ds for other 2 cycles, right. So, once you got dm and ds, so that means after that inductance per phase, the formula you know, L is equal to 0.4605 log Deq upon ds millihenry per kilometer. So, Deq and ds you substitute here and it will be millihenry per kilometer, right. So, upon simplification it is 0.4605 log 2 to the power 1/6, then d upon r dash whole to the power half into d2 upon d3 to the power 1/3 millihenry per kilometer. Further simplification 0.4605 log 2 to the power 1/3 into d upon r dash into d2 upon d3 whole to the power 2/3, then overall to the whole to the power again half. So, this is log. So, this half will come this side, right. So, half in bracket we are putting 0.4605 log of 2 to the power 1/3 into d upon r dash plus 0.4605 log d2 upon d3 2/3 to the power 2/3 millihenry per kilometer. So, this one is equal to, again can be written as L is equal to half in bracket Ls minus m. This is equation 75, right. This way this expression we are writing half Ls minus m, right. Minus m we are writing, that means this part is Ls, right, half this part is Ls. Ls is equal to 0.4605 log to the power 1/3 into capital D by r dash, this is your Ls, and this mutual it is minus taken m. So, m will be 0.4605 log, it will be then d3 by d2, because its minus sign is here. So, it will be d3 by d2 to the power 2/3 millihenry per kilometer.